Today we're going to be looking at matter and the periodic table. There have been different theories over the past centuries as to what matter is composed of. Democritus, an ancient philosopher, talked about atoms as being indivisible particles, particles that can't be divided. Aristotle said that matter was made of earth, air, fire, and water, while Dalton said matter was made of tiny, indivisible particles called atoms, where every atom of a given element will always be identical, while atoms of different elements are different. Thomson experimented with cathode rays and discovered that particles of negative charges called electrons, and he imagined the atom as a positively charged ball with negatively charged electrons stuck inside, like chocolate chips in a cookie. Rutherford, who studied at McGill University, then took that model a little further, talking about an atom that had a small positively charged nucleus containing protons, where electrons traveled in random circuits around the nucleus. And finally, Bohr added to the model, which today is called the Bohr-Rutherford model, where electrons travel in orbits around the nucleus like planets around the sun. So what we know today, that matter is composed of pure substances and mixtures, but the pure substances are composed of elements and compounds. Elements are made up of atoms, while compounds are made up of molecules. Pure substances can be found as elements in the periodic table, or compounds which are combined elements. This is the periodic table, which we will be examining at further depth. Elements are made of smaller parts called atoms. Atoms contain three types of particles: protons, which are positive, neutrons in the nucleus, and finally electrons, which are negative. Protons are positively charged. They are found in the nucleus, and the number of protons is the same as the atomic number of the element. So hydrogen has an atomic number of 1. The chemical symbol is H. The name, hydrogen, and the mass, how much it weighs, is 1.01. Electrons are negatively charged. They travel in orbits outside of the nucleus, and different orbits contain different numbers of electrons. The number of electrons is the same as the number of protons of an element. The maximum number of electrons in each orbit follows these rules. In the first level, there are 2 electrons. Second is 8. Third is 8. And because we study up to the 20th element, 2. How to represent atoms? We can use a Bohr-Rutherford diagram. We draw a circle to represent the nucleus of the atom. We write the number of protons found in the circle, because protons are in the nucleus. For example, hydrogen has 1 proton. We draw curved lines to represent each electron shell, and then we follow the rules, the 2882 rule, to place all the electrons in their shells. And hydrogen has an atomic number of 1 proton. It's balanced, has the same number of electrons, and there's 1 electron in shell number 1. The periodic table consists of different types of elements. And the periodic table was developed to group elements according to their different properties, such as physical properties, such as shape, color, texture, mass, and volume, boiling point and density, as well as chemical properties, how the substances behave when they come in contact with other substances. And the periodic table divides elements in various ways. Metals, nonmetals, and metalloids into chemical groups or families, into periods. So metals, nonmetals, and metalloids. Firstly, properties of metals: they conduct heat and electricity. They're malleable. They have luster. They're shiny. They react with acids. And they're ductile. They are solids at room temperature, and they're gray or silver except for copper and gold, and they are located on the left side of the periodic table. Nonmetals are non-metallic. They do not conduct well. Non-malleable, non-ductile. They are different colors and states. They do not react with acids. And they tend to be on the right side of the periodic table. And finally, metalloids, or semi-metals, share properties of metals and nonmetals, and they are usually found along the staircase. And boron, silicon, Ge, As, Sb, Te, and Po are metalloids on the periodic table. Chemical groups are elements in the same vertical column, and they're part of the same group or family. And elements are organized according to the number of valence electrons. In other words, how many electrons exist in the outer shell. Elements in the same group share properties in common. For example, in group 1, these are called alkali metals. Group 2, alkaline earth metals. Group 7, halogens. And group 8, inert or noble gases. Lewis notation is a simpler way of representing elements, and they only demonstrate the number of valence electrons in the outer shell. So we write the symbol for the element and put dots around the symbol to represent the number of valence electrons. And remember, valence electrons correspond to the group or family. So for example, if we look here at a neon, they would have, it's in group 8, it would have 8 dots around Ne. Periods are elements located in the same period or horizontal row, and they have the same number of orbits or energy levels. Chemical reactions: most elements cannot be found as free elements, and they combine with other elements to form compounds. Chemical reactions, in order to attain a full valence electrons, and that is the goal, they react with other atoms in order to gain a full outer shell. They gain a positive or negative charge, or then are called positive or negative ions. Oppositely charged ions will attract each other and form molecules. So for example, lithium would have a tendency to lose 1 electron, fluorine would have a tendency to gain 1, and that would form a compound. And then it becomes balanced. Chemical reactions: when a chemical reaction takes place, a new substance is formed. The new substance usually has properties that are very different from the elements that formed it. Certain signs tell us that a chemical change has taken place. Signs of a chemical change would be change in color, production of a gas, production of heat and light, formation of a precipitate. And change cannot be easily reversed. Chemical equations a chemical reaction can be represented by a chemical equation. For example, sodium plus chlorine forming sodium chloride. The elements before I'll call reactants, and the elements after the arrow are called products. Law of conservation of matter: matter can neither be created nor destroyed, only transformed. To respect that, chemical equations must be balanced. So for example, these are balanced equations. Over here, to balance such equations, I must make sure that I have the same number of atoms on the left. For example, there are 2 chlorine atoms on the right. I would need to put a 2 in front of this molecule. Now there are 2 sodiums, and then I would have to put a 2 in front of the sodium on the right to balance it. Chemical reactions: combustion. Much of the energy used in the world is produced by combustion, burning of fossil fuels. Once the minimum ignition temperature is reached, a combustion reaction requires two reactants, a fuel source, and oxygen. The reaction produces two products, carbon dioxide and water. The reaction also produces a certain amount of energy. And this is the famous fire triangle, where ignition temperature is required, fuel and oxygen, in order for combustion to occur. Law of conservation of mass. Since all atoms are conserved during a reaction, the total mass of the reactants must be equal to the total mass of the products. So for example, if 4 grams of hydrogen react with 16 grams of oxygen, there must be 20 grams of water produced. Energy, finally, can be renewable or non-renewable. Non-renewable in terms of fossil fuels, nuclear energy, and renewable in terms of hydro, solar, and wind, as well as biomass.